All right, in this section of 5.1 of approximating and computing area, we will take a look at a really basic way to do this and see how it generalizes and extends, and we can actually compute the area underneath of some arbitrary curves that are the graph of a function. So there's some preliminary things that we just want to get out of the way really quickly, which will make it easier for ourselves to build up this theory of integration. For right now, the first thing we're just going to talk about is, let's go ahead and switch gears here. Sorry about that. First thing we're going to do is take a look at these intervals here. All of these intervals, they are just specifying a specific length or portion of the real number line. Right? We could have A and B, and actually whether we choose to exclude or include, we are going to say the distance here is the same. Because a point is zero-dimensional. It specifies a location, but it inherently doesn't have any length or width or area or volume. It's just a location. It's zero-dimensional. Where a length is one-dimensional. An area is two-dimensional. And of course a volume is three-dimensional. But a single point, like one of these vertices, has no length, width, area, volume, or anything. So whether or not we choose to include, such as here where we include A and B, or we exclude A and B, or any combination thereof, the length of all these intervals is the same. It's just the difference, B minus A. Okay, so if we have a rectangle where the one side is A by B, let's say from here to here we've got A and B, and from here to here we've got C to D, then this has an area of the length of the one interval times the length of the other interval. Effectively, what we're going to do here is basically say that the only thing we can really compute the area of exactly, for right now, we're going to assume is a rectangle, nothing else. So, if we want to estimate the area under this curve, so the area between the x-axis here, the horizontal axis, and this curve, one way that we could do it, so we are doing the area under the graph of f between x equals 0 and x equals 2. Well, one thing we could do is just evenly divide this region up. So here it looks like we've got 1, 2, 3, 4, 5, 6, 7, and looks like this distance here is the same. So let's say 8 rectangles. Now I know there's no rectangle here that you can see, but if you notice here, the height of each one of these rectangles, the height is determined by plugging in the right endpoint into the function. See where it stops right here? It's true for all these rectangles, even for this rectangle right here. For this rectangle, the height is the value of the function at x equals 1, right here. That's f of 1. So here, technically, this rectangle has a height of f of 2, which clearly f of 2 is 0. So what we can do is split up this interval from 0 to 2 evenly into a certain number of rectangles. So in this case, we split up this, we can split 0 to 2 into 8 rectangles. Then that means each rectangle has a width of, well, we take the total width of the interval, so 2 minus 0, which is 2, and then we'll divide it by the number of rectangles. So each rectangle has a width of a quarter. So 1 quarter, 2 quarters, 3 quarters, 4 quarters. You get 1, 1 and 1 quarter, 1 and 2 quarters, 1 and 3 quarters. And then we have, well, 1 and 4 quarters, so 2. And then, of course, this provides for us an estimate. And in this case, it is an underestimate because the rectangles are all wholly contained underneath of the curve. So our estimate would be in a underestimate. And, of course, there's a lot of gaps here, so this probably is not a great estimate. But honestly, that does depend on what are we using this estimate for. This might be good enough estimate. Maybe it's not. If it's not enough estimate, all we can do is take the number of rectangles, 8, and increase it. Maybe we can double it and get 16. that would give us a lot more resolution. We would say our partition is finer, and we would realize a more accurate estimation of the area between the horizontal axis and the graph of f. All right. So we're going to skip effectively these two theorems. It's a good thing to read on your own, but as far as the video is concerned, it's not really super important to talk about this in the video. What we will mention here is this remark 1, where the dimensions of area. So for instance, with differentiation, we are familiar that with differentiation, if we have, let's say, meters and seconds on the horizontal axis, then the derivative would have meters divided by seconds. Well, if we find area now, area, we're going to learn in the coming sections that differentiation and this process of calculating area, they actually are inverses to one another. They're almost opposites. So instead of dividing our vertical units by our horizontal units, we are now going to multiply our units together. So in this case, the area here would have units of meter times seconds, so meter seconds. And this example up here, this remark, they say, what if we have seconds and then velocity? Well, here, the area then would be meters per second times seconds, which is just meters. So, dimensions of area, we're going to multiply. And that makes sense, because for a rectangle, right, what do we do for a rectangle for the area? We would do this length times this length. So we're multiplying units together. All right. So the next thing we're going to have here, getting the theory set up, is effectively what happens if we split up this interval into lots of little rectangles. So I didn't draw any here, but let's say we go ahead and draw some rectangles here. Something like that. So here I'm using the right endpoints for those two. Maybe I'll use the left endpoint for this one. And then I'm going to just kind of leave this little area here blank, this area here blank, and then I will continue back up here. Let's say we got a left endpoint, another left endpoint. There we go. And this one right here, for instance, this one, we didn't even use the left or the right endpoint to determine the rectangle's height. We just picked some sample point in the middle. So this x star sub I, and the I just tells you what rectangle you're at. So here, this is x1, so this is like rectangle 1, rectangle 2, rectangle 3. So here, a sub I means it is the area of the ith rectangle. So here, the area of this rectangle, we could say, is A2. The area of this second to last rectangle would be area A sub n minus 1, where capital N is the number of total rectangles we split this up into. So effectively what we do is we take some interval from A to B. We're going to say the very beginning point our value of our interval is x0, and the very end value, b, is the last point. So we're going to number them x0, x1, so on and so forth, all the way up to and including xn. And then, now that we have that, this effectively defines a certain number of rectangles. In this case, I have ellipses here because, well, the number of rectangles, capital N, was let to be arbitrary. So we can't really specifically say what that is, so I'm just going to go ahead and put some dots here. Of course, when you're doing your own examples, it will be a concrete number, and there shouldn't be any ambiguity there. So here we get some formulas. So the width of all of these rectangles are going to be exactly the same. They're all going to have length delta x. So this is delta x equals b minus a over n. Now the height of the rectangle is determined by plugging in any x value between the left endpoint of our rectangle and the right endpoint of our rectangle. Any point would work. So whatever point you choose to use to determine the height, we're going to call that x star. So if we're figuring out the sample point in the ith interval, it would be x star sub I. So we plug this into our function, and that would give us this value here, and that gives us the distance. So it's this distance here times this distance here, which would give us the area of our rectangle. Now this process, we're going to repeat this for each rectangle. We're going to do length times the height, length times the height, length times the height, so on and so forth, until we have the area of all of these n rectangles. And then we will add them all up together. And that will give us an approximation to the true area under the curve. Now, the last thing we're going to talk about here are there are 3 common schemes where you can either, let's look at one of these rectangles in here. Let's look at do this one in blue. Let's look at this rectangle right here from x I sub 1 and x I plus 2. So you can either use the left endpoint, and then that will determine the height of the rectangle. So something like that. So that's what we would say LN scheme, where we're using the left endpoints, and then n here, whatever value you pick, that's the number of rectangles. So L sub 8 would be splitting this up into 8 rectangles. And then we will determine the heights for each of the 8 rectangles by plugging in the left endpoint from the rectangle's width. Instead here, we could also do the what is known as the right endpoint approximation, where we use the right endpoints. We'll get something like that. There's another one that's very common, and that is the midpoint approximation, where here you would first find the midpoint, which is probably right there, and then you'd plug that into the function. So then the height would be whatever that is. Okay? Now, depending on how curvy your function is, the left and the right and the midpoints can really vary and give you different approximations. But the thing we need to keep in mind is, as long as we have a sufficiently large number of rectangles, so in other words, as n gets really big, then whether we use the left endpoint approximation, the right endpoint approximation, the midpoint approximation, or some other scheme, for instance, maybe you choose the maximum height, maybe you choose the minimum height, maybe you choose, not the midpoint, but maybe you choose, the quarter point or the 3/4 point, not the midpoint. Any of those schemes, as long as n gets really big, then all of those schemes, for sufficiently well-behaved functions, they'll all approach the same value. Okay.